It's a simple phase map, and let's see how we can do this. All right, so part A was pretty simple. All you had to do was find the partial pressure of compound X. And why are we finding the partial pressure of compound X? Because the map requires that. So what relationship are we going to use? Yeah.
The partial pressure of compound X is going to be mole fraction times the total pressure.
Sure. And it's that relationship that we use from our ideal gas approximation. And we can plug and chug, and we find that the partial pressure of X for 100 parts per million, the concentration of X is 1/10 10 to the -4 ATMs. And did everyone understand how to find 100 parts per million? Is everyone okay with that? All right. So we get a partial pressure, which is that. What about the temperature of the compound X? Anyone? Fatima?
Oh. 300.
What?
300.
Yeah, simple. X in the air. Simple, give you colors. Alright, so now we have a phase diagram. And let's locate parts, let's find our bearings on this map. So, this is the vapor region. Because we're at a low pressure and high temperature. And if you think about it, if you have a low pressure, there's more space for molecules to move around, and so you're most likely a vapor at high temperatures. So what region is this? Liquid. And this? Solid. What about this line? What is this line? For what? Vapor liquid. Cool. What about this one? Awesome. And what about this point? Triple. Awesome. So you guys have your bearings, and now we need to navigate through this map. All right. Anyone have any suggestions? It's somewhere in this region. Dorothy.
Oh.
I know you know it.
Well, you know you're starting at 300K, so you can find 300 Kelvin.
Yeah.
And then it's 1 times 10 to the -4 ATM of X. And since your y-axis is partial pressure of X, just read off of where 300 and 0.0001 cross.
Perfect. So if people can hear what Dorothy said, we know our temperature, we know our partial pressure, we find where they intersect, and boom, we have our point. Awesome. So now that we have our point, we need to find our temperature. X will first start to condense. So anyone have any suggestions how we can do that? Britt?
We'll move that way. So downward toward temperature, keeping pressure constant, and when it hits the liquid and vapor line, that's when it'll start to condense.
Awesome. So since we're keeping our pressure constant and just changing temperature, we'll move along the horizontal line to reach our equilibrium line, and we get our point, and then we go down to find our temperature, which is 182 Kelvin. Sweet? One thing you guys should know is that the y-axis is on a log scale, but the x-axis is on a regular scale, so don't get confused. So you guys just learned how to read this, and so you should remember that you're reading the scales differently. Okay. So we know that we want a contamination level of 10 parts per million, and so we can use a similar technique we used in part A to find the partial pressure at that contamination. Now, what temperature do we need to cool our X to get to that level of contamination? Suggestions? Dan. What can we do?
Wait.
So we're changing our temperature. Dorothy.
Well, you want to reduce it by a factor of 10, so you follow the equilibrium line down to 0.001.
Perfect. So we want to follow our vapor-liquid equilibrium line past the triple point into our solid vapor onto our solid vapor equilibrium line until we get to our point. So we're going along the line in order to get to our point, and our temperature at that point is 162 Kelvin. So notice how we didn't go down and then to the right, or left and then down. We followed our equilibrium line, and that's a key concept. Okay, so now we're at 300 Kelvin, and we want to compress the gas, and we want to find the minimum pressure at which it will first start to condense. So what do we have to do now? Anyone on that side? Dhruv, suggestions?
We'll condense when it reaches the liquid.
Right?
Yeah.
So what Dhruv is trying to say is if we go all the way up on the constant 300 Kelvin line until we reach our equilibrium line, we can find the minimum partial pressure of X at which we will first start to condense. And that pressure happens to be 0.2 atm. And we're done. Are we? Maxine?
That's the only pressure, so you have to calculate that pressure.
Correct. So what Maxine said is we found the partial pressure of X, but what the question asks is the total pressure when X will first start to condense. And we use the same relation we used in part A to find our total pressure, but now we know our concentration and we know our partial pressure, and we use that to find our total pressure with 2,000 atms, which is super, super high.
And that's not there. You should be able to see it's that there are 10 times 10 times 10 times 2. Can you show us that? We're start at the green point and go up times 10.
Times 10 is here.
Times 10 and 10 and 10 times 2.
So yeah, 2,000. And you couldn't do this if you had a regular plot. You couldn't even see this. And so this is the real big advantage of having a log scale. All right. Now this is a pretty cool question. How can we get to 10 ppm just by changing the pressure? Did anyone have time to think about this? Risako, suggestions? You don't have to be right. Just any suggestions?
What did you say? I think, so you have to keep you want to get the partial pressure to be, I think 10 to the negative, or 10, wait, no, the partial pressure is going to be 0.2.
Why can't we do this? We go down, right? We found this to be our concentration.
Oh, really?
Yeah, we can do that, right? No, we
okay.
can't. Because why can't we do this? Are we?
Because it's still 100 ppm, you're just multiplying it by a lower total pressure.
Perfect. So we're trying to reduce our concentration in the gas phase. And if we do this, we're still at 100 ppm, you're just reducing the total pressure. So, in part F, we did compress it until we first started to condense. And what if we increase the pressure even more? Then more of the X will condense, leaving less of X in the vapor phase. And so that way we can get our concentration and find our pressure. So how do we do that? If we go back to our graph, we know that we're still going to be at 0.2 atms for our partial pressure, but we're increasing our total pressure till we get our desired concentration of 10 parts per million. So we know our partial pressure is still 0.2, but we know our new concentration is 10 parts per million. And if we do the calculation to find the total pressure, we find that it's increased by order of magnitude of 10, so it's not 20,000 atm. And I found this really cool resource on the internet that you can go to and check out how phases change when you increase pressure on a map like that. So I recommend that you look at that. Any questions? Good? Awesome.